This is the B-2 Spirit, arguably the most advanced bomber ever built. Its ability to appear from nowhere and strike any target on Earth is the stuff of legend. But what the headlines don't show you is the incredible, obsessive work that happens before it even leaves the ground. This aircraft is a $2 billion masterpiece of physics. Get just one of the thousands of steps in its preparation wrong, and it becomes the world's most expensive lawn dart. Today on the Deep Dive, we're not looking at the bomb drop, we're looking at the invisible, high-stakes mission that happens on the ground to make that moment possible. It all begins here, in a building so climate-controlled it feels like a laboratory. They aren't just building bombs, they're assembling precision instruments. The guidance kits on these JDAMs are incredibly sensitive. Even a speck of dust or a hint of humidity can throw them off. The temperature is locked at a precise 68 degrees. This isn't for the comfort of the technicians. It's for the ring laser gyros inside. These gyros are so sensitive that a temperature swing of even a few degrees causes them to drift. And a drifting gyro means a bomb that misses its target. The first step is attaching the guidance section. Inside is a GPS antenna and an inertial measurement unit that can detect movements smaller than a human hair. The critical part is the umbilical connector, the data cable that lets the B to talk to the bomb. The technicians use torque wrenches with surgical precision to loose, and vibration shakes it apart. Too tight, and the housing cracks. Then, they attach the tail kit with its independently controlled fins. Before any bomb leaves, they run the fins through a full range of motion. If a fin sticks for even half a second, the bomb could miss by 100 feet. Finally, they weigh the finished weapon. The B-2's computer needs the exact weight for its ballistic calculations. A 5-pound difference changes the flight path. But throughout this entire process, one rule is absolute. The weapon is kept completely inert. The fuse is unpowered. The guidance kit is in test mode. It cannot, under any circumstance, detonate. The thermal battery that powers the fuse is designed to only activate when it experiences the massive force of being ejected from an aircraft. Until that moment, it is, in every practical sense, just a very sophisticated, very expensive piece of metal. Once the weapons are ready, we turn to the aircraft itself. And this is where the job goes from mechanical to almost artistic. The B-2's stealth isn't magic. It's a carefully shaped surface designed to absorb or deflect radar energy. And that surface has to be perfect. The B-2 is covered in a radar-absorbent material that's as fragile as a chalkboard. It contains tiny ion spheres that vibrate when hit by radar, converting the energy into heat. But this coating is delicate. Rain, hail, or even a bird strike can damage it. Low observable, or low, technicians examine every inch, looking for chips, scratches, or bubbles. A gap as wide as a credit card at a panel seam can act like a beacon. When they find damage, they don't just paint over it. They sand it down with precision tools, mix special compounds that cure in minutes, and carefully apply them. They then sand it again, removing material in thousandths of an inch. The final surface can't vary by more than the thickness of a few sheets of paper. They aren't just fixing a plane, they're sculpting it. Once the aircraft passes its stealth inspection, the weapons are finally brought over. Unlike other bombers, the B-2 can't carry anything externally. Everything must go inside. The massive bomb bay doors open, revealing the rotary launcher. Think of it like a giant revolver cylinder, holding up to 8 2,000-pound weapons. This entire assembly can spin in seconds, bringing each bomb into release position. Load crews use hydraulic lifts to raise each bomb and lock it onto suspension hooks. The mechanical and data interface has to align perfectly. Miss it by the width of a penny, and the weapon won't receive power or targeting data. They connect the umbilical cables, allowing the aircraft's computer to talk to the bomb. Even now, the bombs remain inert. The coordinates aren't loaded yet. That information stays in the B-2's secure computer until moments before release, allowing the crew to adapt to changing situations in real time. With the plane loaded, attention turns to the pilots. The B-2 flies at altitudes where a loss of cabin pressure would be instantly fatal. So, specialists in the aircrew flight equipment shop prepare the gear that keeps them alive. They test the pressure suits and oxygen masks, ensuring they deliver air even under high G forces. The helmet alone is a marvel of technology. with heads-up displays and visors that can go opaque in milliseconds to protect the eyes from the flash of a nuclear detonation. They inspect every detail of the survival vest, the emergency beacon. The signal mirror everything a pilot might need if they have to eject over hostile territory. On a mission that can last over 40 hours, this gear isn't a luxury, it's an operational necessity. Before the crew even arrives, one of the most dangerous jobs on the airfield takes place, the hot pit refuel. For a quick turnaround, there's no time to shut down the engines. The B-2 sits there. It's for engines idling, each one hot enough to melt aluminum. Fuel crews, wearing silver proximity suits for protection, approach like astronauts on an alien world. The first, most critical step is grounding the aircraft. In flight, it builds up a massive static charge. One spark near the fuel vapors would be catastrophic. They clamp a thick grounding cable to a bare metal point on the landing gear. Then, they connect high-flow hoses, pumping 167,000 pounds of fuel at 600 gallons per minute. It's not just about quantity though. The fuel must be distributed perfectly across the tanks to keep the flying wings stable. Too much weight in one place, and this tailless aircraft becomes unstable. Finally, the pilots arrive. They climb in and strap into ejection seats that are survival systems unto themselves. They connect to the aircraft, and the startup begins. The B-2's cockpit is all digital displays. The mission computer has more processing power than the entire Apollo program. The first thing it does is align its inertial navigation units. For 8 minutes, the aircraft cannot move an inch. The ring laser gyros are measuring the Earth's rotation to establish their position in space. Any interruption, and they have to start over. As they taxi, the flight computers make thousands of corrections per second just to keep the plane stable. Without them, this flying wing would be uncontrollable. At the target, the crew runs the final checklist. The bay doors open for a fraction of a second. As the bomb separates, the umbilical breaks, and the JDAM finally wakes up. Its thermal battery ignites. Its fins unlock. Its internal computer processes the targeting data, GPS coordinates, wind speed, air density, and calculates a flight path. It doesn't just fall straight down, flies a precise curve, making hundreds of tiny corrections with its fins, guided by satellites in its own internal sensors, with a technician in a climate-controlled room, torquing a bolt to an exact specification. The B-2's mission is famous, but the real story is the silent, obsessive, and incredibly detailed work of the ground crews who make the impossible look easy. It's a reminder that in the world of modern warfare, the most critical battle is often won on the ground, before the aircraft even takes off. Thanks for watching the deep dive. If you want to understand the technology shaping our world, hit that subscribe button.